Okay, so welcome to the weekly tutor session 4, and today we will go through all the weekly problem set 4. Maybe this session will longer than 1 hour because we have several really hard problems. Okay, so for the first question, we have V variables and R registers, and we can assign at most 2 variables to one register like this. And of course, we can assign none of them to this. And the position in one register does not matter. So like if we put V1 at first or the V2 at first, these two things should be the same. So basically for this question, we want to find some recursive equation to solve everything. So we can just define PVRB with V variables and R registers, how many kind of assignments we can have. So let's try to find the base case. The first one is really easy. If we have 0 variables, then no matter how many registers we have, we always have only one way to assign, just assign nothing. Another base case is also easy. Suppose we have more than 2 variables. Then it means that we cannot assign all the variables to the registers. So there's no way to find the assignments. Then with these two base cases, we can go to the recursive step. If we consider the last register, there are 3 situations. The first one is it's empty. So we can just remove that and got P V R minus 1 because we need to use the left R minus 1 registers for the V variables. And if we just assign one variable to that register, then we have P V minus 1 and R minus 1. Yeah. Because we need to remove this variable with the register together. And also we have we choose one ways to choose such variable inside the register. So of course this one is equals to V P V minus 1 and R minus 1. And for the last situation, this one is also easy, just it has two variables. So we have we choose 2 ways to choose the 2 variables and we can remove them as well. So V minus 2 and minus 1. So the answer is we just add the 3 cases together, and this is our answer for the first part of the first question. Is there any question for this part? Okay, seems no, then let's continue. For the next part, we don't want we have any empty register. So let's define a similar thing which called P prime. So here everything else is the same except we don't want any empty register. So what is our base case be like? First of all, this one is 0, right? Because if we have 0 variables, then no matter registers we have, there should always be 0 way to get a variable inside the register. But we want to define that officially maybe. So let's try to write something like this. So P prime V R equals to 0 if V is smaller than R. Because if we have less variables than registers, then it's impossible to assign one variable to each register. So we have this base case. And also we know that if we have one variables with one registers, or we have 2 variables with one registers, then we only have one way. Just assign everything to the register. So basically these two things is our base case. And for the situations, they are just the same thing, except we don't have this situation because we don't want an empty register. So for the first one, we choose 1 and P V minus 1 R minus 1. And the second one, we choose 2 P V minus 2 and R minus 2. R minus 1, sorry. And we can add them to get the answer for this one. So this question is done. Any question for this one? Okay, seems no. Then let's go on. Next question is much more interesting. So basically, if we consider each student as a vertex, and if A and B are friends, we can add an edge between them. So we can have these two things. The first one is something like this. Suppose A and C are friends, we can add an edge between A and C like this. And then we know that B is their common friend if B connects to both A and C. And we know there are L kind of B based on the question. Also, suppose if A and C are not friends, so there's no edge between A and C. We have M kind of B which connect to both A and C. So basically, and we have this equation. This is the left part and this is the right part. We want to show why this equation holds. Oh, this one is question 2. We just finished question 1. We just begin question 2. Okay. So basically, if we want to show that this equation holds, we can simply show that they represent the same thing. So what's the left part represent? Okay, here we can show that they both represent to this one. This means suppose we are given some vertex A, and we want to find how many pair of B and C exist, so that we find A connect to B and B connect to C, but A is not connect to C directly. Why the left part is equal to the number of this one? Let's first consider how many B we can have. As we know that everyone have K friends, which means we have K possible B, so which here is a K. And then how many C we can have? First, every B have K friends also, so we have K friends, we can have K things connect to B. But among the K things, L of them is also connect to A because we know here. L of C, L kind of B is also connect to A, so we need to minus L first. And also A cannot come to connect to itself, so we also remove A here. So we have K minus 1, K minus L and then minus 1 kind of C to be choose. So we have totally K times this one. Then if we consider it in a different way, let's first think about how to choose C. As totally we have n number of vertex. Among the n vertex, there are K vertex directly connect to vertex A. So they cannot be C because C should not connect to A. So we minus K first. And then among the left thing, it includes A itself. So we need to remove it also, which means we have n minus K and minus 1 number of C we can choose. And then for each kind of such C, how many B we can choose? Here we know, right? If A and C is not connected, then we have M kind of B for each such A and C. So we have M possible B. Okay, then we are done. This one is also represent to the pair of B and C if we given A. So we know these two represent the same thing, and that's why the equation holds. Okay, any question for this one? Okay, the left side again. Okay, that's okay. So basically, we know A and we want to know B and C. Yes, I will post all the solution later. So consider as we know A, then how many kinds of B we can choose? A have K friends and B should connect to A. So we have K possible B. And for each B, it also have K neighbors, have K vertex connect to B. So maybe we can have K possible C. But we don't want C connect to A. So any common friends of A and B cannot be C. How many common friends of they have? They have L common friends, so we need to remove L first. And also, we cannot choose A as C. And among the K neighbor of B, it includes A. So we need to minus 1, which represents A. So we have K minus L minus 1 times of C we can choose. That's why we multiply of this. And then this means the number of BC we can choose in all. Is that okay? Okay, cool. Then let's go to the next question. Next question is much harder, to be honest. And basically, we have 8 boxes, and each box we want to put 6 balls with different colors. And for each pair of color combination, we don't want it to appear real to more than one box. So suppose we have one color 1 here and color 2 here in box 1. Then it cannot be appear real in any other box. Only 1 is okay, but if 1, 2 are appear real together, then it's not okay. And we want to use as little number as color as possible. So the first idea is always want to reuse the color as many as possible. So let's first fill some color 1 to every box. Then there is a problem you may find. If we do so, then suppose we have put the next ball in B1, and then we cannot put the color 2 to any other box because 1 is already there. No matter we put it to which one box, it will appear real to 1, 2 again, and then which is not allowed. So which means if we do so, then all the other balls should be distinct. And that will make us use a lot of different colors, and we don't want that. So what can we do? Suppose this happens, then we want to use less 1. So what can we do? We can simply change this 1 to 2, right? And also we can change this 1 to 2. And suppose we already fill all the other things, and this one will not influence any other thing. Because as we know, there used to be 1 here, so there must be no 2 or any other colors in box 1 here. So we can simply replace the 1 to 2 here freely. If you notice that, then we can make a claim like this. Suppose if we reuse the color so many times, we want to reduce some number of it. We can just change it to another color which just appear real once with it. So if we notice this one, and we want to apply this as many as possible, we can get this solution. You can try yourself, but just try to apply this claim as many as possible, and you can always finally achieve this one. And here you can see that we have totally 23 number of colors. Oh, why 3 times? Good question. And in fact, you can choose 4 questions or 5 times. Any times is okay, but just like if you try to apply this again and again, you will find that when you achieve 3 times and you want to move it to 2 times, the the number of color you use will not reduce anymore. So, so basically, this is just got by try. You can first try to remove as many as possible and until the color you use is not reduced. You can first fill this thing like reuse some color in 8 times and reduce the 8 and then to 7 and then to 6 and try it until to 3 and then you can also try to 2. Not really, but you will always need to first find some solution to show that this is okay. But then you need to prove that this one is a minimal thing. We are in the first step of this question. Because if you don't have a exact solution, you cannot show that this one is a minimal thing. So we need to always construct something and show that this one is minimal. We are at the first stage. We are construct this solution. And then we want to prove that no other solution is better than this one. To be honest, yeah, of course it's not. I feel this is kind of the hardest question in this problem set. We are just at the first stage. So maybe let's go on. For now, we know that we have a solution with 23 kind of colors. Why this one is the best thing? Let's use something different. Let's define SL as a set of colors in box I. And the total number of colors can be represented as this one, right? Because we have 8 boxes, so we want to the union of the 8 sets, the set of the union of 8 sets, and by the PCI, the principle of inclusion and exclusion, can got something like this one, and of course dot 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 dot. But till now, this one is also hard, and we don't know how to solve this, right? What can we do? Let's try to check something interesting. Let's first suppose there is some color appear in 5 boxes. Then what will happen? Let's still use this graph. Suppose color 1 is in the 5 box, the first 5 box. Then what will happen? All the other color in this area should be distinct, right? How many colors are left? Each of the box will have 5 colors left, and we have 5 boxes, and then we have one color for this color 1. So we already used 26 colors, which is already more than 23. So we know that no color in 5 boxes. Okay, then what about 4? What about 4 colors? So similarly, we try this one, and we can get something like 5 times 4 plus 1 equals to 21. Okay, seems this one is okay, but then let's consider how we can construct the box 5. Okay. We cannot use 1 because we have shown that there is no 1 here. So how many colors we can reuse in B5? So let's 3, 2, 3. Oh, that's maybe 2, 3, 4, 5. We can reuse 2, we can reuse 3, we can reuse 4, we can reuse 5. But we still need 2 more colors, right? We still need 6 and 7 because we need 6 balls. And none of these colors should be appear in the first 4 boxes. So we already have 21 plus 2 is 23 colors, and we still need to fill the other 3 boxes. So which shows that also no color in 4 boxes. In other words, all the things in the following part is equal to 0. Right. We only need to consider the first 3 terms. That would make this question much more easier. After we show that, we can try to go detail in this expression. If we allow, so firstly, how many of these? This one is the most easiest part. We have 8 sets, each set contains 6 balls. So it's equals to 6 times 8 equals to 48. Then what's the maximum value of this one? Okay. Yeah, correct. At most, what's this number? But 7 and 1 times 2, 20. Yes. So we want to 8 choose 2, which means we want to we have at most this number of sorry. We have at most this number of things inside this term. So for now, what we have? We have 48 minus 28 and plus the 3 term. Si, Sj, and Sk. We can replace this one as 20 directly. Till now, seems it's still hard to do this. But for now, as we want the color as small as possible, so we want to use as I want to reuse all the colors as many as possible. So in my ideal way, all the colors should be used 2 times or 3 times. So what can we state that? How many colors is used 2 times? We can state that we use 48 minus 2 in colors 2 times. Why? Oh, sorry. We use 48 minus 2 in colors 3 times, not 2 times, because suppose we use all the colors either 2 times or 3 times. Then if we use in colors, then totally we use 48 balls. So we can use this one to show that all the else is the colors used only 3 times. And if we do so, then we can replace this as here. So what we have got finally? Remember n equals to this one. So we have n equals 20 plus 48 minus 2n, which means 3n equals to 68, sorry. Yeah. And here we cannot use equal. Why? Because we use many. Oh, why we don't count in fact we need to consider that we want to reuse them as many as possible because we want to reduce this size, right? If we consider several only use 1 times, then this one should be larger. And if this one is larger, then this one is larger. And we use some estimate things, so we need to use larger than or equal instead of equal directly. Suppose if we just use some color 1 times, and we will reuse other colors more times, right? Otherwise, we will provide more colors. So the ideal way is all the color is used 2 times or 3 times. As we show that if we use more than 3 times, it's worse. But if we use some color only 1 times, then we will use something more colors in 3 times, and then this value will be larger, and then this value will be unchanged, and then which means n will be larger. As we want to keep this size smaller, we want to keep the number of use 2 times larger. Is that okay? Okay, cool. So finally, we got this equation. Oh, sorry, this is 68, not 48. Oh, what happened to me now? So if we calculate this, is it 22 point whatever something? I forgot this number, but it's 22 point whatever. So as n is the integer, so this one we can just replace this as 23. So for now, we have shown that n should be larger than 23. And we have given solutions that n have exactly 23 colors. So we can come to our conclusion that there is only 23 colors is valid and it's the minimum number of color we can use. Is that okay for this question? Any other question about this? Okay. Okay, so first, do you understand why I can show that there's no more than 4? Okay, then the question is still why there's no 1 times, right? Okay, before we come to this one, we already got something like n is larger than this one minus this one and plus this one. So no matter what other things we change, this one will be unchanged. So basically what we want to do is just reduce the size of this one as many as possible. So that's why I say that we want to reuse as many colors 2 times as possible, because if we only use other colors as 1 times, then we will need more colors used 3 times. Just consider if we don't use other colors 2 times, then why we not just use more 3 times color or 4 times color? Because the only thing like stop us use more color than 3 times is because we need to use distinct color here. So if we don't reuse other colors, then we can just keep using something like this or something like this, reuse the color several times, and then put all the distinct color in this area. But the better way for us, we want like something like 1, 1, 1, and then what happened? Okay. The best way we want, to be honest, is something like 1, 1, 1, and then we put 2, 2 here, and then we can put 3, 3 here, and then 4, 4 here, and then 5, 5 here, and 6, 6 here, something like this. So this can really save us, right? And then maybe we can put 7, 7, 7, something like this. Because if we stop reuse these things, we will just create more colors. But if we use more 3 colors here, then this value will be larger. So we want to use as 2 colors as possible. So the ideal way is just use only 2 or 3 instead of 1. Is that okay? Okay, cool. Let's go to next question maybe. For question 4. Okay, this question. Before we do that question, I want to show you another question in book. Can you see this one? Okay, cool. This question is the easier version of the problem set. This question is in our textbook. We can first try this one and then reduce our question to this question. In this question, we have n plus 1 real numbers which are between 0 and 1. And we want to show that 2 of them are among this thing are small. The difference between them are smaller than 1 over n. And this one is really easy. Consider we divide the range 0 to 1 into n in separate slots, which is this one. From 0 to 1 over n, and from 1 over n to 2 over n. And then finally until this one. Here we have n slots. And we have n plus 1 numbers. So at least 2 numbers should be in 1 slot, and the difference between them cannot be larger than 1 over n. This one is easy, but why this one is connected to our question? We only have number x, and we even don't know its range. But here is the interesting thing. We can try to construct such set, like we can use 1 times x, 2 times x, 3 times x, and until n plus 1 times x to create such list with n plus 1 elements. And then as we only want to consider the thing between 0 and 1, so we can just check the fractional part of this one. Let's say like we use this one to show that it's a fractional part of 1 times x or I times x. And this one should be between 0 and 1. Why we can do so? Because finally we want to prove something like this. And if we multiply q at both sides, we can get something like this. And p can be any number. So we can just set p as the integer part of qx, and then take this one as the fractional part of qx. Then here is easy. Now here is easy now. As we know that we have n plus 1 elements in the list, then we must kind of find 2 things with ix and jx so that the fractional part of them are inside the same slot, which means this one is smaller than 1 over n. Then we can simply set q equals to I minus j or j minus I, just depends on who is larger. And p equals to the fractional part of I minus j times x. oh, sorry, let's say like something like this, the integer part of that. And then we just got the same thing. Okay, you mean this statement or this statement? Oh, okay. So basically, this is not a. Basically, here it's just take the fractional part, which means support I times x is equals to something like a b c point d e f, like 100.123, something like that. And we only take about the fractional part, which is 0.123. So here is why we say that this one is between 0 and 1. Because here we only take the fractional part. So as long as, because why we can do so, as we have already changed our requirement to this one, so we can use any p. So we can use p as the integer part, and by do so, this one can directly convert to the fractional part of 2 times x. Because we can just choose p as the integer part and remove that. That's why if we choose it to the fractional part of qx and we got this one, it's the same question of this one. We have already done. Okay, cool. And then for next question, we have another question in textbook. And I want to show you this one first, which is much more typical. So basically, we still have 1 to 2n, the 2n elements, and we want to find a subset with n plus 1 size. And here we want to show that there are some a and b so that a can divide by. Remember in our the question in our problem set, the question is suppose find some a must b so that a is not divided by b for any ab. What's the maximum size? So if you know this question, even you don't know how to do that, you can directly give the solution that it's a. But why? So basically, if we need to first prove that for n plus 1 it's not work, and then we want to give a set with exactly n elements, and no one can divide with each other. So let's first do the first question is this one. So basically, we can divide the twin elements into two sets. One is E, which contains all the even elements, and another is O, which contains all the odd elements. And we can directly show that each of them with n elements because totally we have twin elements there. And we can show that for all elements in E, or we can say for all elements in A, we can write something like this. Why? Because suppose there is some element, let's say it's some element k. If it's already odd, we can say that it's equals to 2 power 0 times O, which O equals to E, O equals to E. Because k itself is the odd number. And if k is not, we just divide k by 2 and see if it's odd. If no, then another 2 again, and another 2 again, and another 2 again. So finally, it will always go odd, or it's no otherwise. So which means we can represent all the elements into this kind of thing. Then another interesting thing is that suppose we have two elements which with the same odd value inside it. So we can represent as these two things with 2 power k1 and 2 power k2. Then one of them can divide by another. This one is also easy to say, right? We can just remove the O. So then what will happen? We have n kinds of O here, but we have n plus 1 elements. So there must be some elements equals to these two things, and they can divide, one can divide by another. So we are done about proof this one, and we will show that n plus 1 is not valid for our question. Remember, our question is when we want to find the maximum set of subset with no one can divide by another thing. So we know that n plus 1 is not okay. But if n is okay, how can we construct such one? Here is a really easy way to construct such set. You can simply do it with n plus 1, n plus 2, n plus 3, and until 2n. Inside this set, this will have n elements and no one can divide by another. Why? Because 1 is not inside it, and if we want to divide by, if A want to divide by B, then it means that B is, this is easy to see that, right? Because, okay, because if we want to B is the multiplier of A, then another multiplier will be at least 2, if we don't want A is equal to B. But here, no one is larger than 2 times than the other one, because the smallest element is n plus 1 and the largest element is 2n. So this inside subset is valid. Then we can know that for this answer, for the answer for this question, the answer is n. Is that okay for this question? Okay, cool. Then let's go to next one. Okay, we want to show that there's multiplier of n, some k in which only appear real with digit 1 or 0. Here is how I do that. First, I will create a list with 1, 1, 1, 1, 1, 1, 1, 1, 1, and until with n plus 1 ones. So the size of this set is n plus 1, right? So let's write something like this. And then what can we do? We want to find n holes for this n plus 1 pigeons. Then the most common thing we can think is about is we can check the remainder if they divide by n. Because if we divide by n, we only have n possible remainders. So with n remainders, that's just n possible remainders. So there are at least 2 of them with the same remainder. Let's say call them k1 and k2. Okay. So k1 can equals to an plus r and k2 equals to bn plus r, where r is the common remainder of them. And let's suppose k1 is larger than k2. Then what is k1 minus k2? K minus k2 is equals to a minus b n plus r minus r, which equals to a minus b times n. But what's the value of this one? Remember, k1 is like 1, 1, 1, 1, 1, 1, many ones here. And k2 is also 1, 1, 1, 1, many ones here, but it's smaller than k1. So the difference between them is 1, 1, 1, 1, blah, 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 1, and then 0, 0, 0, blah, 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 0. So this one is valid in our question, and then this one equals to this one. A minus b is the integer, right? So we find such number and we are done. Is that okay for this question? Okay, next one, another really hard question. Okay, for this one, I want to show that there is some subset AS interaction AJ so that it's equals to 1. And all the AI is equals to 3. with the n numbers and I is smaller than n plus 1. So here is what we want to show. So we want to prove that by contradiction. So we want to first show that there's no such a and aj, so that's the intersection part of them with size 1. And another thing we want to first state is that the n mass is much larger than 4. Why? Because we want to have n plus 1 subsets, different distinct subsets. But if and each subset with size 3. But if we only have 4 numbers, then we only have 4 possible subsets, which is smaller than n plus 1, which is 5. So we know that n much larger than 4. With these two ideas, then let's begin. We have n plus 1 subsets, and each set will have 3 elements. So if we allow repetition, we have 3n plus 3 elements there. But we only have n elements in all. So according to pigeonhole, there are at least one element appear real in 4 sets, right? Because equals to 3 point whatever. So let's just assume that that element is element A, and the 4 set is A1, A2, A3, and A4. Then we just give 3 elements in A1, which is ABC. And remember, we want no two set with intersection sets is equal to 1. So, and no two sets should be the same. So we want this one be ABD because we want to reuse A and B. And for A3, for the third set, we can be either ABE or ACE, just like reuse AB or reuse AC. However, if we consider we use ACE here, and let's first consider this case. And we know that A is also in A4, right? Then what else can we choose? If we choose B, then we have to choose another one. But we have to choose C or E because we don't want to only have one difference with A3. However, this is not okay because so if we don't choose AB, what can I do? We can choose AC. But also if we already choose AC and we have to, if we don't choose B, we have only one difference with A2 then because A2 only have A. A2 don't have C and other things. So with this thing, we know that this one is not valid because we cannot construct such A4 with only one difference. Then we know this is ABE and ABF. This is the only possible way. Then if we do so, we will have an idea. For other sets, we can divide it into 2 parts. Either it have A and B, or it have none of A and B. Okay, with this idea, suppose among them there are T subsets with A and B, and there are n plus 1 minus T sets without A and B. These 2 parts should be totally disjoint. Why? Because each subset only has 3 elements. Suppose it's not disjoint like this with something A, B, C, and there's another set with C, but they cannot with A, B, so we'll have something else, CXX, XYX2. Then there is only one set 1 intersection, which is not allowed because we don't want this one for now. So these 2 parts should be totally disjoint. Then how many elements are there in here? We have T elements, each one contains A, B, and will provide another distinct elements. So we have totally T plus 2 elements there. And then here is N minus T minus 2 elements there. But we have N plus 1 minus T sets there. Okay. So we can simply state that N prime equals to N minus T minus 2. And also there's no 2 sets we want to have the intersection set with only 1. Then again, we come to this question again, right? We have a new in, we have some new sets, but we still keep this question. And if we just try to do this again and resolve this again, we will have in prime prime. So in prime A is larger than in prime, and we will have in prime prime is smaller than in prime. And then what happened? Infinite descent. So basically this one is impossible. Then that's why we think that the contradiction is formed and this one is impossible. So this one is true. Is that okay? Descent? Yeah, I prove that with infinite descent because I show that if this one can be solved with this way, then we will create this problem again with the smaller n. And if we solve it again, we will create another smaller n and then another smaller n. So if it has a solution for this kind of situation, then we will infinitely solve this question again and again and create some new smaller n and smaller n and smaller n. And n is always positive and is a natural number, so that's not possible. Okay, for next question. For question 8. Okay, so basically we still want to do two things. We want to first construct some answer and then show that this answer is the best, is the maximum way. So as node 1, I should be get another one inside this element. The most natural way is just create the larger part of this because 1, 2, 3 until 25. We just choose the larger part of this, which is from 13 to 25. In this subset, the size of it is 13. Right. So then I want to show that this one is really maximum one. So let's show that by contradiction. Suppose we have some larger subset like this. And then we can find another subset with called S prime prime, which include all the elements which inside S prime but not in S. And we know that S prime prime should be smaller than 13 because all the elements inside S prime prime should originally not in S, and only 12 elements not in S originally. So we know that the size of S prime prime is smaller than 13. And we can also order the S prime prime in the decreasing order so that we can do something like this. And got EI is larger than EJ for all the I smaller than J. With this order, we can got something like this. Because all the number is which is larger than 13 is already in S. So the largest one in S prime prime should be smaller than 13. So we can write something like this. And then we will try to add the elements in S prime prime into S. And if we can do all of these things, we will finally convert S into S prime. So suppose we first append E1 into S. Then we'll find that all the three elements are in S. But this one makes this list not valid because E plus 13 is equals to 13 plus E1, of course. It's all the three are inside S. But at most, two of them should be inside S prime because S prime is a valid list. So we need to remove one from 13 or 13 plus E1. If we remove 13, then when we append E2, we will find this list. E2, 14, and 14 plus E2. And if we remove 13 plus E1, when we append E2, we will find this triple. E2, 13, and 13 plus E2. Which means, and if we again remove one and go on, remove one and go on, whatever, finally, it will always find this triple because we know that set of S prime prime is smaller than S, which means when we append one element into S, we need to remove at least one element. However, when we finish appending all the elements in S prime prime, this S should be already equal to S prime. But the set of S is unchanged during the appending process. Because when we append one, we need to remove one. So we got like this. And this one is wrong. So which means that, or maybe you can write like something like this one. So with this idea, we can show that S is already the maximum thing. And here we got S is 13, so we know that the answer is 13. Is that okay? Okay, for question 9, suppose we have 6 digits. Then how many kind of lessons we can have if we need any 2 lessons should have at least 2 different digits. Here is the idea. If we can first use pigeonhole to say that if we have 10 power 5 plus 1 lessons, then that will not work. Why? Because suppose we only consider, we can separate all the kind of lessons in based on the first 5 digits. And the first 5 digits can give 10 power 5 possible ways. Then it means that if we have 10 power 5 plus 1 pigeons in the 10 power 5 holes, at least 2 pigeons should be in one hole. Which means there are at least 2 lessons will have the same 5 digit, first 5 digit. Then their difference should only appear real in the last one, which is not valid. So we show that 10 power 5 plus 1 is not a lot. Then what about 10 power 5? How can we do that? Here, let's try to construct this way. Okay, suppose we just give random way for the first 5 digits A, B, C, D, E, let's say. A, B, C, D, E. And for the last digit, we can just add the sum of the first 5 digits and check the value of them more than 10. Why this one is valid? As we only have 10 power 5 kind of lessons, we can ensure that none of them have the totally same first 5 digit. So we only consider 2 cases. The first case is they have more than 2 difference in the first A to E. If this one, then it's already done. And the second case is if there is only 1 difference between A to E. Then let's say that F1 is the sum of the first number of the first 5 digits, and F2 is the sum of first 5 digits of the second number. Then the difference between F1 and F2 should be smaller than 10, right? Because they have only 1 digit difference, and all the other things are the same. And 1 digit is from 0 to 9. So which means the value of them F1 mod 10. So suppose if F1 is not equal to F2 and F1 and F2 should have the same mod 10, what does that mean? That means F1 equals to F2 plus 10 times something, 10 times K maybe. Or maybe we can write like F1 minus F2 equals 10K. So this 2 thing is equivalent. But as long as the difference of them is smaller than 10, so this situation is not possible. Which means the last digit of them should be different. Then they have 2 different digits, and this one is okay. Okay, is that okay for this question? For our last question, we have 9 points in the 3D dimension. So each coordinator should be looks like x, y, z. It's 3 values. And we want to show that at least one segment should contain one integer coordinator. Then how can we do that? Consider for each number, we have only two parity things. One is even and one is odd. Of course, so with three number, how many parity situation can it have? For x, it can be even or odd. For y, it can be even or odd. For z, it can be even or odd. So totally 2 power 3 equals to 8, right? There are 8 possible parity property for this coordination. But we have 9 points with 8 possible parity situation. So pigeonhole again. There are at least 2 points with the same parity thing, which means we have x1, x2, or y1, z1, and x2, y2, z2. And both x1 and x2 should be even or odd. So do y1 and y2, z1 and z2. But how can we use that? If they are both odd or both even, then we can always ensure that x1 plus x2 is even. So do y1 plus y2 and z1 plus z2. Because odd plus odd is even, and even plus even is also even. Then this question is easy now. Because we know that all the sum of them are even, so we can simply do this one. Plus y2 over 2, and the last one is z1 plus z2 over 2. This coordinator is like in the middle point of the such of these 2 points. Like if this point is like here, then this coordinator is like the middle point here. And this one, as this is even, this is even, and this is even. So these three things should all be integer. And hence we found such point. Okay, is that okay for this question? Or any other question about this weekly problem? Okay, if no, then here we have 2 more questions, which is in our Google Sheet. The first one is about the format of exam, and you will see that later in the Canvas, but I can give you first. So we will have 5 questions in all, and you only need to choose 4 of them to solve. Choose which it depends on you, but you need to mention that. And also another question is how much time you need to spend on each question, and that totally depends on you. You may just want to solve the first 3 questions and just drop the last 2 questions maybe, or you want to solve all the 5 questions just to challenge yourself. That's all depends on you. So this is the 2 questions in the Google Sheet, and I can give you the answer. Okay, seems that's all. And if you don't have question, we can stop this session. And I will later post the recording and also post the official solution to the Canvas. Okay, then bye. Have a nice weekend. See you.